Hi, welcome to my channel, JaberTime, where I do math videos from algebra to calculus and differential equations. If you're new here and you like this video, consider subscribing and hit the like button. And if you have any comments, leave them down below. This is my second time recording this video. First time I uploaded it, I looked at it a few times and I didn't like much the way I explained the whole thing. Math is so simple once you see it, and maybe I went too fast. So I'm redoing it. I'm trying to slow down and show you what I'm talking about through more detailed graphs. Hopefully you like it. Hopefully you'll see what I see, as it is simple. It's that simple, by the way. Most of the math, once you see it, it's so simple. Let's get started and let's talk about linear approximation and differentials. I'm gonna talk about a few things. This is a focus, keywords, let's say topics that I'm gonna talk about. We're gonna approximate the value of f of x from a line L of x, and that's gonna be f of a, the point that we are considering the tangent to be at, plus some difference f prime of x multiplied by x minus a. In this case, delta x and dx will be the same. Delta y will be f prime of x delta x, and delta y will be also the difference between the two values. Kind of hard to understand what's going on here without graphs, so I'm gonna do it with graphs. Next semester I'm teaching also 250A, which is vector calculus or calculus 3, and we do have the same topic but in 3 dimensions. So we're going to have delta x and delta y and delta z. If you are interested, in the next semester I'm going to upload a new one for linear approximation. Alright, now linear approximation and differentials. To approximate f near x equals a, we're going to use this. This is the main summary of this video. F of x will be approximated to the value from L of x as the following: f of a plus f prime of a times x minus a. This graph says it all, but if I keep looking at this graph and I keep moving my mouse to show you what's going on right here, it's not going to be that clear. Let me give you an overview, then I'll slow down and I'll show you the details. This is a, this is x, which is a little bit more than a. We're moving to the right, so we call it delta x. So a plus some difference in x value will be called x. This point is a and f of a. This point right here is x and f of x. Now, there is too many details right here, but in short, from this y to this y, there is a difference. It's called delta y. So this difference right here is called delta y, where this difference right here coming from the tangent and the derivatives that we're using, it's called dy. When they say approximate f of x to L of x, instead of f of x we're going to write L of x. That means instead of this value as an output, we're going to use this value as an output. Okay, I think we have an idea, so let's move on. So let's focus on this right triangle. As I said, we're going to go from this x, which is a little bit more than a. So if a is 1 and we add 0.05, it's kind of hard to graph it that much and call it 0.05, but we extend the graphs to show more details. It's just like a small difference. So this would be 1.05. This point right here will be f of 1.05. If I take this value instead, I'm under approximating the actual value. If the graph is concave down, the tangent will be above. This way, my approximation will be over the actual value. All right. So this is delta y, and this is not delta y, it's called dy. But it has more details right here. It's called f prime of a delta x. Now, this is the whole package. This is what we have, but we're going to use this approximation, which means we're losing this value. So the main thing is this right here instead of the actual, and that's what we are losing. Differentials. Let f be differentiable on an interval containing x. A small change in x is denoted by the differential dx. If it's not that small, we call it delta x. When x or delta x goes to 0, we call it dx. That's the language of calculus and differentials. So dx is very tiny. We're looking at delta x approaching 0. Pretty much that triangle, it's hard to see anymore. As a limit, as a concept, delta x approaches 0. So we call it in short in our writing dx. The corresponding change in the y value in f is approximated by the differential dy. So instead of delta y over delta x, we call it dy dx, and that becomes the slope of the tangent instead of the slope of the secant. Now dy equals f prime of x dx. This is like a quick summary, then I'm going to slow down with the graphs. That is delta y, the difference between the 2 points on the graph, will be instead approximated and replaced by dy. So delta y is approximate to dy, and delta y is approximate to this much right here, f prime of x dx. That's near a. Now here's the graph on one slide, the whole graph. This is f of x all the way. That's called actual. We're going to take this point instead. That's called linearization. Instead of the curve, we're using the line to approximate the value at this point, which is a little bit more than a, where we built this tangent. So delta y will be replaced by dy, and that's right here. So far, I'm going slow, as you could see, because I want you to notice the notations one by one. I repeated myself a few times that we are approximating this value. Instead, we are using this value. And that's called linearization, L, which came from a tangent at A. Now, one more time. This much is called f of a. This much right here is the actual f of x at x, which is a little bit more than a. So a plus delta x is x, or differently, delta x is x minus a. Now this much right here, we, instead of applying it or doing it, plugging in the number in the original function, we could use linearization and end up at this point. So, one more time, this is delta y. This is f of a. So the actual will be coming from f of a plus delta y. But what is delta y? Delta y is f of x minus f of a. This whole thing is f of x. This much is f of a. So that's delta y. Delta x is x minus a. I mentioned that in the previous slide. So we are agreeing on delta x. and we are agreeing on delta y. So instead of going with the whole thing, we're gonna go f of a plus this much instead, but that's not gonna be delta y, that's gonna be approximate to delta y. This is called in math dy, not delta y. Delta y is all the way up to this point from this point. Now, looking at this right triangle that I highlighted for you in green, because I want you to focus on the green part right here mainly. This is delta x, and this is not delta y. But this line has a slope. It's a tangent line at a f of a, right there. That has a slope. The slope of the tangent line at a is f prime of a, which is differently called dy dx at x equals a. And it's called rise over run, and it's called dy dx, because we are taking it from a secant to this tangent. As you could see, we move it to become a tangent. When we apply the limit, we call it dy dx. What does this say here? It says the following. F prime at a is dy dx. Excuse me. Dy is f prime times dx. But dx right here and dy right here as a rise and run tells me from the previous pictures that dx is the same thing as delta x. So the dx and delta x are the same, but delta y is not the same as dy. So I could replace dx, which came from a cross multiply, if you could say so. I could replace dx by delta x. But we agreed on delta x to be that difference, so it's x minus a. So far so good, right? We have f of a, and we have this much instead to approximate, but this much is actually f prime of a times x minus a. This right here pretty much explains the whole picture of linear approximation. Notice that I'm making a dashed line right here, telling you this is not the actual. I'm reading it from L of x. If this is x, this point or this height is L of x, where this height all the way up here is called f of x. So we are replacing f of x by lower amount, which is called L of x. This is called approximation. It's an approximate, it's not an actual output for the location x. Alright, now this much is dy, it's not delta y. I keep repeating myself, as you could see, which we agreed on to be f prime of a dx or delta x or x minus a. So L of x, the output for this point up here, is L of x. All the way up to the black curve, it's called f of x. This is actual, this is approximate. I'm using different colors to show you the difference between them. This is all the way exact point. If I stop right here, I'm using approximate, and it's less than the actual. What is L of x? This much is called L of x. To me, on the graph, it's two pieces. This piece and this little piece. That is f of a, and that is f prime of a times x minus a. right there. That says it all. That says that if you want to approximate f of x and replace that with L of x, you are using approximation. So if you want f of x and you want to approximate, you could, instead of writing L of x, you could write this sum of two items, and the graph says where they're coming from. It's f of a and f prime of a multiplied by x minus a. So with all these slides, with all these pictures, what you need to take with you is the following. We approximate f of x close to a. If we are close, we are more accurate. If we are far, we are not approximating correctly. Imagine if you use this tangent line and you started at 1 and you don't want to go to 1.05, you want to go like to 17. Well, 17 is so far from 1, and the tangent will be so far away from the curve because the curve could go away. That's not called a good approximation. In higher math and different math, we use the percentage of error, and there is more into it. I can't make the video like an hour video for this, but later on in the future I will be adding more videos, and I will be calling them part 2 and part 3 and so on. So this is what you need to take with you. Instead of f of x, we're going to read it from the line, and that was 2 parts on the graph, and that should do it. Here's 2 quick examples, because most of the examples are the same. I don't want to repeat myself a lot, but I picked 2 different ones to show you what's going on. What is delta y that we're going to use instead of dy, and what is the equation of the line that's called L of x. Example number 1. Approximate the change in y. How much the change in y, where y is called f of x in general, to x to the 9th minus 2x plus 1, when x changes from 1 to 1.05. We have the start point, which is a, as 1.00. We are going from here to here. That is called a difference of delta x, which is 0.05. F prime of x will be the derivative of this, which is 9x to the 8th minus 2. Delta y will be replaced by dy, and that's the word approximate delta y. If you want to replace delta y with dy, you saw on the graph, that's not the same. Delta y, dy are not the same. Delta x and dx are the same. So instead of delta y, we're going to write dy. That's dy. F prime at a, which is at 1, just plug in 1. Delta x, which we agreed on as 0.05. And you end up with 7 times 0.05, which is 0.35. That's how much delta y is being replaced by dy. dy is about 0.35. And if x increases from 1 to 1.05, then y increases by approximately 0.35. Here's a bonus. We don't have to discuss too much detail, but I just want to show you the idea. If you want to go all the way to f of x at 1.05, you will end up with 0.451328, and there is more, but I stopped at 6 digits. F of 1 is 0, so the change in y, the actual change in y, is 0.45. Well, the approximation gives me L of x, that's a 0, it's not going to change anything. F of 1, 1 to the 9 minus 2 times 1 plus 1, that's 1 minus 2 plus 1, which is 0. So the reaching up to the line, the tangent line, you're gonna reach up with a distance or a value of 0.35, where here the distance is, or the value, the difference between f of 1 or f of a and f of a plus x or a plus delta x, I mean, is 0.45. So the difference is about 10%. That's what we're doing as an approximation. So if you use approximation, we are losing 10%. Pretty much, that's like if you're under or above. If it's concave up or concave down, we are losing about 10%. My final example, I don't have to slow down too much. I just want to show you the equation of the line that's called L of x. Find the linear approximation to f of x equals x to the third minus 5x plus 3 at x equals 2. In other words, they just want you to find the equation of the tangent to the curve at x equals 2. That's pretty much it. Sounds like fancy when they say linear approximation, but now we understand it. Instead of staying on the curve, we just, if you're close enough on the tangent line, you take it from the tangent line and we call it approximation. So here's f prime. That's f prime at 2. That means this is the slope of the tangent. L of x is f of 2 plus f prime times x minus 2. 1 plus 7 times x minus 2, which is 7x minus 13. Does this remind you of something right here? Well, if you move the f of 2 to the other side, it becomes like delta y, right? Does this look like a point slope form? Any way you look at it, you're just finding the equation of the tangent line at 2. That's it. That's a slope of the tangent line, and that's the y-intercept. As simple as that. Hopefully it was worth it. I took the video down after I watched it. Sometimes, when I have some time, I go back and forth and see, like, if I'm doing something that I could learn from and improve. And I visit my videos to see if there's any comments also. I noticed that I was going a little bit too fast, hoping that because it's so simple, I didn't want to slow down. But I felt like, you know what, I'll just take it down and I'll slow down, repeating myself with the graphs, and make it simple, or try to deliver a simple concept through a graph, because it is so simple. The whole math is simple once you see it. Once it clicks. I like the comments from students sometimes when they say, that's it. I go like, yeah, that's it. So anyway, that should do it. Thank you for watching. And if you feel that I did a good job delivering, simplifying what is linear approximation, leave me a comment below. Any comments, I really appreciate it. I just want to keep improving and do my best. Hopefully within a year, I'll add way more videos that from my classes that I teach. I started like 2 months and a half, 3 months now, and I have like 45 videos up. That says a lot. Those videos are not like 5 minutes to 8 minutes. They're like 25 minutes to 45 minutes. So imagine if I keep doing this in a year from now, how much math I'm gonna have up. On top of that, I'll be improving also on the audio, lights, and beyond. So if you are new here, hit the like button if you like it, leave me a comment, and subscribe if you haven't yet, and I'll see you in the next one. Thank you very much for listening and for watching. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.